All right. Today is Friday, May 11th. We're getting real close to the end of the year here, so we're just moving through these things rather quickly. Today, what we did was we talked about Avogadro's law and Boyle's law. We talked about the problems that we had, although there was very little talking. Not much to say about those. Basically, those are pretty simple algebra. You just have to make sure your pressure units match and your volume units match. And you have to make sure you've calculated number of moles. Okay. Today, what we're doing is we are talking about Charles' law, and we're talking about Mr. Gay-Lussac's law. He's a Frenchman, so you have to say it with a French accent. Actually, they're both French scientists. And we spent quite a bit of time today doing gas law demonstrations. I'm probably not going to get those taped tonight, but I will get those taped and posted as soon as possible. Homework tonight. What you really want to do is you want to make sure you read up on the kinetic molecular theory in your textbook. That'll speed things along. It's all conceptual, which means the more times you see it, regurgitate it in your mind, you got to kind of ruminate on it a bit so that you understand what's going on. Otherwise, you're just going to regurgitate it and not understand it. Gosh darn thing. All right. The other thing tonight's homework: Charles' law and Gay-Lussac's law. Here we go. Charles' law. Charles never actually published his law. It was first published by Joseph Louis Gay-Lussac in 1802. Joey there, he credited Jacques Charles with coming up with this law in 1787. Now, Jacques was actually a balloon enthusiast, a hot air balloon enthusiast, if I remember right. And he came up with this gas law by working with hot air balloons. This should come as no big surprise to you then when we talk about it. All right. What Charles notices is that when pressure and moles are constant, that if you want to increase the volume of a balloon, you increase its temperature. And if you want the hot air balloon's volume to decrease, which you don't often want unless you want it to land, the temperature is going to decrease. You know what? We all know that from going to birthday parties at Chuck E. Cheese in the middle of winter and getting balloons. You walk out in the middle of winter with a balloon, with a helium balloon in your hands, and it starts shrinking up. Temperature decreases, volume decreases. You get a little bit upset about that, but as soon as that helium balloon warms up again, temperature increases, then the volume increases again. Okay, so there's nothing terribly tricky about this. Notice it is a direct proportion. Volume and temperature are directly related. This is just like Avogadro's law yesterday. Volume over temperature is equal to volume over temperature. Now, if you are very good at math, or you're at least good at predicting things, you should be able to predict what this graph is going to look like. That's right, direct proportion relationship graph. So we get a nice diagonal line. Notice as volume and temperature go up, the other go up. So as volume goes up, temperature goes up. As temperature goes up, volume goes up. All right. The big important note here is this one right here. Ooh, that did not work right. The big important note is right here. Temperatures have to be in Kelvin. If you use Celsius or you use Fahrenheit, you are going to get negative volumes. The possibility of getting a negative volume exists. And that doesn't make much sense. What does a negative volume look like of a gas? Yeah, it doesn't look like anything. You can't figure that out. So we'll talk about that more on Monday, why we have to use Kelvin. But for now, that should suffice. Okay. It doesn't look like the video is going to play, but you can remember what the liquid nitrogen video looks like. Balloons going into liquid nitrogen. All right. Now, Joseph Louis Gay-Lussac is a French chemist. He's a French scientist. Around the 1800s is when he came up with his idea. And basically, he's also a hot air balloon enthusiast, if I remember right. He notices that as the pressure on a gas increases, the temperature also increases. And as the pressure decreases, the temperature also decreases. Now, most of the times we actually are. A good example is where we are messing with the pressure. And the temperature changes. If you've ever had one of those aerosol cans that is used to dust electronics, dust a keyboard, dust some sort of electronic device, it's just basically got compressed nitrogen inside of a canister. So we've got a spray canister here. I'm going to do my best to draw this. Here's a spray canister. It looks kind of like a spray paint can, except for it says it's got air in it. Okay. Now the gas that's in here is under high pressure. Okay, very, very large amounts of pressure. What happens when you actually push on the valve here is that the gas comes out, but now it's under low pressure. So if it's under normal temperatures under high pressure, then when the pressure decreases, what should happen to the temperature? As the pressure decreases, the temperature decreases, and it actually shoots out cold air. They say not to flip it upside down and press the valve, because this is mostly air in here, which is 70–80% nitrogen. The nitrogen actually leaks out, gets on your finger. Well, that's a good way to get rid of some warts on your finger. If you were thinking about the math on this, same math as you think it's going to be. It's a direct relationship, so P1 over T1 equals P2 over T2. If you're trying to think about what's going to happen here, this is definitely the graph. The graph is still a direct relationship graph, so we still get a nice diagonal line. The only real issue here, again, temperatures must be in Kelvin. Basically, the reason for that is if one of these temperatures is negative, then that means that pressure is going to have to be negative. That doesn't happen. There's no such thing as negative pressure. Pressures are always positive. They always push one way. The harder side always pushes towards the weaker side. Okay, that's about it. We just have some gas law demos. If you wanted to, you could actually go back and use this YouTube clip right here to check out what happens to a railroad tanker when you increase the temperature and then you increase the temperature of the inside of it and then you cap it off. What happens? As the temperature is hot, as it gets colder, what's going to happen to that pressure? It's kind of interesting. Watch it, find out.